Tonight, we're going to explore one of the most unsettling questions in modern science. Not whether humans can reach Mars, but whether human bodies can ever truly belong there. For decades, we've treated Mars as humanity's next home. The rockets are being built. The missions are being planned. The biggest challenges are usually described as engineering problems waiting to be solved. But what if the greatest obstacle isn't technology at all? What if it's us? For more than 60 years, scientists have studied what happens to the human body beyond Earth. We've watched bones lose density, muscles weaken, vision change, and the immune system behave in unexpected ways. Yet through it all, one assumption has quietly survived: that Mars has just enough gravity, enough to keep the human body healthy, enough to raise children, enough to build a permanent civilization. But what if that assumption is wrong? A 150-pound astronaut would weigh only 57 pounds on the Martian surface. The gravity that shaped every organ, every bone, and every cell in the human body over billions of years simply doesn't exist there. Not for adults, not for unborn children, not for the generations that would have to follow. By the end of tonight, you'll understand why settling Mars may be less of an engineering challenge than a biological one. How gravity, radiation, and human development converge into a single unsettling conclusion, and what our future beyond Earth might actually look like. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Think about what the body is doing right now. Your heart pushes blood through roughly 60,000 miles of vessels. Your kidneys filter around 200 liters of fluid every day. Your immune system patrols 37 trillion cells, each one running thousands of chemical reactions per second, following instructions encoded in 3 billion base pairs of DNA. That code was written over 4 billion years. Not by engineers, not by designers working toward a goal, by the slow, grinding pressure of one specific environment, selecting what worked and eliminating what did not. The body is not a general-purpose survival machine. It is an Earth machine, built for Earth's gravity, Earth's magnetic shielding, Earth's atmospheric pressure, Earth's radiation protection. Remove any one of those inputs, and something starts to break. The question is not whether that breakdown is dramatic. Usually it is not. It is quiet. It is gradual. And in many cases, it does not stop when the stressor is removed. We know this because we have 6 decades of evidence. Since the early years of human spaceflight, researchers have tracked what happens to the human body when it leaves this planet. The data is not theoretical. It is measured, recorded, and in many cases, deeply unsettling. Astronauts aboard the International Space Station have lived in microgravity for continuous stretches exceeding 400 days. The Russian cosmonaut Valeri Polyakov holds the record for the longest single spaceflight in history, 437 days aboard the Mir station, returning in 1995. Every person who has spent extended time in space has returned with measurable biological damage. Not anecdotal complaints, measured changes in bone density, muscle mass, cardiovascular function, fluid distribution, and vision. Some of those changes resolved over months. Some persisted for years. Some never fully reversed. Here's what scientists observed consistently. The body does not simply pause in space and resume on return. It responds. It adapts. But the adaptations are not improvements. They are compensations, and when the original environment is restored, the compensated system does not always find its way back. Scott Kelly's mission is one of the clearest examples. Kelly spent 340 days aboard the International Space Station, returning in March 2016. Researchers followed him closely afterward, comparing his biology to his identical twin brother Mark, who had remained on Earth. What they found was unexpected. Kelly's telomeres had lengthened during the mission. Telomeres are the protective caps at the ends of chromosomes, something like the plastic tips on shoelaces that keep the threads from unraveling. In general, longer telomeres are associated with cellular health. Shorter ones are associated with aging and disease, so the lengthening sounded at first like a beneficial effect. Like space had somehow slowed the clock. It had not. When Kelly returned to Earth, his telomeres shortened dramatically, not gradually, rapidly. They fell below the baseline measurements taken before his flight. The system had overcompensated in one direction and collapsed in the other. Think of a metal rod, bent under sustained pressure. When the pressure is released, the rod does not spring back to its original shape. It holds a deformation. The cellular machinery that manages telomere length had been stressed by the spaceflight environment and could not maintain equilibrium after the stress was removed. The change persisted for years in some cell populations. Kelly was back in Earth's gravity, back in Earth's atmosphere, back in the environment his body was built for. And the damage remained. That is the pattern across the evidence base. Not one isolated case, not one unusual individual, every extended mission, every long-duration crew member, a biology being asked to operate outside the parameters it was written for, and paying a cost that does not simply disappear when the parameters are restored. Now consider Mars. Mars has gravity. That matters. But here's where it gets strange. Mars' gravity is 38% of Earth's. The surface acceleration on Mars is 3.7 meters per second squared. On Earth, it is 9.8 meters per second squared. The difference sounds manageable, and the intuitive image is almost appealing. A person who weighs 150 pounds on Earth would weigh 57 pounds on Mars. A person who weighs 200 pounds would weigh 76 pounds. Lighter, easier to move, less strain on the joints. The romantic picture of a Mars colonist bounding across the red landscape with something close to superhuman ease. That picture is precisely backwards. Earth's gravity is not an inconvenience the body would be glad to shed. It is a required input signal. Blood flow is calibrated to it. Bone density is maintained by it. The vestibular system, the inner ear mechanism that tells the body which way is down, depends on it. Muscle tone is constantly regulated against it. Every time you stand, walk, shift your weight, or simply hold your head upright, your body is receiving and processing gravitational load. That load is not optional. It is not background noise. It is data. Remove 62% of it permanently, and the body begins making the same kinds of compensatory changes it makes in microgravity. Slower perhaps, but in the same direction, and likely without reversal, because there is no return flight, no restoration of conditions. Mars gravity is what you have, for the rest of your life. 6 decades of research have shown what partial gravity exposure does to human biology over months and years. The evidence from extended ISS missions, from Polyakov's 437 days on Mir, from Kelly's 340 days in orbit, gives us a measured picture of a biology under sustained gravitational stress. Mars gravity is not the same as microgravity, but it is not Earth gravity either, and the body knows the difference. The question for a temporary Mars mission, one lasting a year or two, with a return to Earth, is difficult but potentially solvable. Careful exercise regimens, pharmaceutical interventions, countermeasures designed and refined by decades of space medicine research might keep a crew functional long enough to complete an exploration mission and come home. But that is not the question of permanent settlement. Permanent settlement means no return. It means children born on Mars, developing under 38% of Earth's gravity from before they draw their first breath. It means generations that would never know Earth's conditions. It means asking whether human biology can sustain itself, reproduce and propagate indefinitely in an environment it was never written for. That is a fundamentally different question. And across 3 independent lines of evidence, the answer begins to take shape. The gravity evidence is only the first line. Bone listens to gravity more directly than any other part of the body, not as a passive structure, not as scaffolding that simply holds a shape. The skeleton evolved specifically to resist gravitational loading, and it maintains itself only by doing so, continuously, every day, for an entire lifetime. Remove that loading, and something goes wrong that no amount of determination or medical intervention has fully solved. Here is how it works. Every time a foot strikes the ground, a wave of mechanical force travels upward. Through the tibia, the long bone of the lower leg, through the knee, into the femur, up through the pelvis, along the spine. The skeleton is not just absorbing that force, it is reading it. Embedded inside bone are specialized cells called osteocytes. They sense the strain passing through the bone matrix around them and send chemical signals outward. Those signals activate a second type of cell, the osteoblasts, the cells responsible for depositing new bone material. At the same time, a third type of cell, the osteoclasts, is continuously breaking down old bone, regardless of what signals are or are not present. The process that converts mechanical stress into biological activity has a name: mechanotransduction. It is the skeleton's way of listening. Gravity speaks, bone responds. Take away the loading, and the conversation stops. Osteocytes receive no strain signal. Osteoblasts deposit nothing. Osteoclasts keep removing. The balance tips, and it stays tipped. Day after day, the bone matrix thins without being rebuilt. We know exactly how fast this happens in microgravity, because we have been measuring it on the International Space Station for decades. Astronauts in orbit lose roughly 1 to 2% of their bone mineral density every month. Not over a career, per month. After 6 months aboard the ISS, the weight-bearing bones, the lower spine and hips, have lost 10 to 12% of their density. The femoral neck, the narrow strut connecting the thigh bone to the pelvis, shows some of the most severe degradation of all. It is the exact region where fractures become catastrophic. Those numbers belong to people in microgravity. Mars is not microgravity. Mars has gravity, 38% of Earth's. And there is a tempting assumption built into that fact. If microgravity causes severe bone loss, and Mars provides some gravity, perhaps Mars colonists would land somewhere in between. Perhaps they would stabilize. Perhaps the body would find a new equilibrium and hold there. Damaged but functional. But something was wrong. The assumption about a safe middle ground does not hold. Partial gravity data is thin because neither the ISS nor Earth can easily reproduce 38% gravity for controlled experiments. The ISS delivers microgravity. Earth bed rest and water immersion simulate weightlessness, not partial loading. Mars-level gravity is genuinely difficult to study, but the direction of the physics is not in doubt. Less load means less signal. Less signal means less osteoblast activity. Less osteoblast activity means net loss. The rate would be slower than in orbit, but the process would be the same process. A reasonable extrapolation puts monthly bone loss on Mars at roughly half the microgravity rate, perhaps 0.5 to 1% per month. That sounds manageable. Work through the arithmetic. After 1 year on Mars, a colonist has lost 6 to 12% of skeletal mass in the weight-bearing bones. After 5 years, 30 to 60%. Year 10 is, as researchers have described it, difficult to contemplate. And then the critical question, where does it stop? This is the reveal that changes the shape of the problem. Bone loss does not continue until the skeleton simply collapses. It stops when the remaining bone mass is adequate to sustain the load being placed on it. On Mars, that load is 38% of Earth's. The skeleton will reach a new equilibrium eventually when the bone density left is just sufficient to handle what Mars demands. Think of a weight-bearing wall slowly losing material through erosion. The erosion does not stop at the wall's original strength. It stops when what remains is just barely enough to carry the far lighter load that presses on it now. The wall is still standing, but you could not build the original house on it again, and you could not restore it without the original bricks. That equilibrium point is not healthy bone. It is not a Mars-adapted version of healthy bone. It is structurally inadequate bone. Bones that can manage Mars, bones that could not manage Earth. For astronauts who return from the ISS, mechanotransduction reactivates when they land. Full gravitational loading resumes, osteocytes begin receiving strain signals again, osteoblasts restart deposition. The recovery is slow and incomplete, but it begins. The conversation with gravity picks up where it left off. Mars colonists would never return. The degradation would be permanent, progressive, and there is no exercise regimen that changes this conclusion in any meaningful way. Resistance training and loaded exercise do slow the loss. Researchers have worked hard on this, but no protocol replicates what Earth provides for free: constant, always on loading through every step, every stance, every moment of upright existence. The body cannot be fooled into believing it is standing on Earth when it is not. The problem does not stay inside the bone. Bones are not only structural, they are also factories. Packed inside the interior of bones is marrow, the tissue responsible for producing the body's most essential cellular components. Red blood cells, which carry oxygen to every organ. White blood cells, which form the foundation of immune defense. Platelets, which control bleeding and initiate repair after injury. As skeletal mass falls, marrow space falls with it. Less bone means less room for the marrow that makes these cells. The body's capacity to oxygenate its own tissues drops. Immune defenses weaken, healing slows, ordinary wounds become more dangerous. Infection risk rises. The skeleton's decline does not stay contained in the skeleton. It moves outward, propagating into the body's most basic maintenance systems. This is what gravity's absence looks like inside the body. Not a single dramatic failure. A slow, compounding erosion of one system, pulling the next system down with it. Bone is the clearest case. The numbers are measured. The mechanism is understood. The math is unforgiving. But the skeleton is only one part of what gravity holds together. And the second line of evidence reaches into a system most people would never expect gravity to touch. Bone is not the only tissue that listens for gravity. Muscle listens too. And it has been listening for a very long time. The body is careful with its energy. Muscle tissue is metabolically expensive to maintain. It burns fuel constantly, even at rest, even when it is doing nothing at all. Evolution's answer to this expense was simple and efficient. Muscle is maintained only when it is used, not as a policy, not as a preference, as a biological rule. Stop using a muscle and the body begins dismantling it, reclaiming the energy cost, redirecting the resources elsewhere. This is not a flaw in the system. On Earth, it almost never matters, because the system is never truly idle. Think about what gravity demands of a body simply standing in a room. The legs are braced against the floor. The back is holding the spine upright. The core is stabilizing against constant micro-shifts in balance. Every step adds more. Every staircase, every bag carried, every moment of simply being vertical is a small resistance event. Continuous and near imperceptible. The body is being trained all day, every day, by the weight of itself. Gravity is not a burden the muscles overcome. It is the signal that tells them to remain. Remove that signal, and the rate of loss is startling. In microgravity, some muscle groups lose approximately 5% of their mass per month. The losses concentrate in exactly the muscles that fight gravity. The legs, the lower back, the deep core. These are the systems most calibrated to the one thing that is now gone. The International Space Station carries a piece of equipment called the Advanced Resistive Exercise Device, or ARED. It is a sophisticated machine designed to simulate squats, deadlifts, and heavy resistance movements in weightlessness. Astronauts spend roughly 2 hours every day using it. 2 hours of deliberate, structured, intense exercise every single day, with no days off. This is not casual fitness. This is a medical intervention, a daily countermeasure against a process that begins almost immediately upon arrival in orbit. And here is where the math becomes uncomfortable. Even with that intervention, astronauts still lose muscle mass and strength during long missions. 2 hours a day on the best available equipment only slows the loss. It does not stop it. The deficit remains. On Mars, the numbers shift, but the direction does not. Walking on Mars involves only 38% of the gravitational resistance that walking on Earth provides. Every squat, every climb, every load carried does proportionally less muscular work. The postural muscles are still being asked to hold the body upright, but against a far lighter demand. The signal is reduced, not eliminated, reduced, and the body, calibrated by billions of years to a different gravity entirely, will respond to that reduced signal by reducing muscle accordingly. Colonists could exercise, they could build gyms, they could dedicate time every day to resistance training designed to compensate for what Mars cannot provide. For some individuals, during some periods, This would help. But here is the gap that the logic of mitigation cannot close. A permanent colony is not a research station. It is not a crew of carefully selected, medically supervised astronauts operating under institutional mandate. It is thousands of people living ordinary lives across generations. Workouts get skipped. Equipment breaks down and waits for parts. Children grow up in bodies that have never known full gravity, and no one imposes a daily exercise protocol on children indefinitely. Life demands time and energy, and daily intensive resistance training competes with work, with illness, with care, with exhaustion. Adherence to any daily physical regimen decays across a large population over years. It decays faster across decades. It does not hold across generations. The cumulative result is not a crisis moment. It is a slow gradient. A population whose muscular capacity declines year by year, whose work output diminishes, whose ability to respond to physical emergencies, to lift, to carry, to endure, shrinks incrementally. The colony would still function. People would still move. But the reserve would be gone, and emergencies rarely arrive when reserves are full. The cardiovascular system carries the same logic one step further. The heart pumps blood against gravity every moment of every day. And standing upright means fighting gravity in two directions simultaneously. The brain sits roughly 18 inches above the heart. Blood must be actively pushed upward to reach it. The feet sit roughly 4 feet below. Blood must be actively prevented from pooling there. The system that manages this is layered and precise. Heart pressure. One-way valves in the veins of the legs that prevent backflow. The calf muscles, which squeeze blood upward with every step. The arterial walls, which adjust their tone continuously to regulate flow and pressure. Every part of this system was calibrated, not after birth, not in childhood, but during fetal development, against a gravitational constant of 9.8 meters per second squared, the same number that has governed life on this planet for billions of years. In reduced gravity, blood moves differently. It redistributes upward. The heart and the sensors that monitor fluid volume read this shift as excess fluid, as though the body is overfull. The kidneys respond logically. They increase urine output. They shed fluid. Plasma volume, the liquid portion of blood, drops by 10 to 15% within the first few days in orbit. The body has correctly identified a signal and responded correctly to that signal. The problem is that the signal was false, and then the heart itself begins to change. With less gravitational resistance to pump against, the left ventricle, the chamber responsible for driving blood out to the entire body, begins to remodel. It becomes more spherical, less elongated. A more spherical ventricle is less mechanically efficient at pumping. The walls of the arteries, no longer stressed by the full demands of Earth circulation, begin to thin. The cardiovascular system is adapting. The word sounds reassuring. It is not. Returning astronauts confront this directly. When they stand after months in orbit, many experience orthostatic intolerance, a condition in which the cardiovascular system, recalibrated for low gravity, cannot immediately cope with standing upright in Earth's full gravity field. Dizziness, fainting. The body that had adapted must now readapt. Recovery takes weeks to months. The system can rebuild, because Earth gravity is there to rebuild it. Mars colonists never return. For them, the remodeling toward a Martian cardiovascular profile is permanent. Reduced maximum cardiac output. Reduced reserve. A smaller engine in a body that still occasionally needs the larger one. This is the reveal that the word adaptation obscures. Adaptation sounds like success. It sounds like the body finding a solution. But biological adaptation to a lower demand is not optimization. It is a downgrade. The heart that has adapted to Mars is barely adequate for Mars at rest. It is not adequate for Mars under stress, for a colonist fighting infection, for a worker in a sudden emergency, for anyone who needs the system to perform at its ceiling rather than its floor. And muscle and heart are only two of the systems carrying the same degraded signal. The third line of evidence has not yet arrived, and it touches something most people would never think to connect to gravity at all. Two systems remain. And then the question has to change entirely. The inner ear contains two structures that most people have never thought about in connection with gravity. The first is the otolith organs, small chambers lined with hair cells and coated with tiny crystals of calcium carbonate. When the head moves, the crystals shift, bending the hair cells, and the brain reads the angle and acceleration. The second is the semicircular canals, three fluid-filled tubes curved in different planes. When the head rotates, the fluid lags behind, pressing against sensors at the base of each canal, and the brain reads the rotation. These two systems together are the vestibular system, and the vestibular system does not operate alone. It integrates constantly with vision, with proprioception, with motor control, with spatial reasoning. Every movement the body makes draws on their combined output. The system uses gravity as its reference signal, not as an occasional input, as the fixed baseline against which everything else is measured. Think of a thermostat that has been calibrated to one temperature. Every decision the system makes, every adjustment, every correction is calculated relative to that setting. Change the setting, and every decision downstream changes with it. On Mars, the vestibular system would recalibrate. Not immediately, but over months and years, the brain would learn that 38% gravity is normal. For a colonist who arrived as an adult, that recalibration would be incomplete and disorienting. For a human born on Mars, the recalibration would be total. They would have no bodily sense of what Earth gravity feels like. The thermostat would be set to a different temperature from birth. And because the vestibular system is woven into vision, into balance, into spatial cognition, the altered calibration would not stay in the inner ear. It would propagate outward into every integrated process. That is the setup. Then the data shifted. Of all the systems that gravity degrades, vision is the one that feels least connected to the problem. Muscle, bone, heart, balance, those connections feel intuitive. Vision does not. And yet NASA rates the damage to vision among the highest long-duration health risks in human spaceflight. They gave it its own name, Spaceflight-Associated Neuroocular Syndrome, SAENS. The mechanism begins with fluid. In Earth gravity, fluids are pulled downward. The body distributes cerebrospinal fluid, the clear liquid that cushions the brain and spinal cord, according to a pressure gradient shaped by that downward pull. In reduced gravity, that gradient changes. Cerebrospinal fluid accumulates around the brain and optic nerves. Pressure builds inside the skull. That increased intracranial pressure pushes on the back of the eyeball, distorting its shape. A healthy eye is roughly spherical. Under chronic elevated pressure, the back flattens. The geometry of vision changes. At the same time, pressure on the optic nerve causes direct damage to the nerve fibers that carry signals from the eye to the brain. The numbers are not abstract. More than half of astronauts who have spent 6 months or longer in space show measurable changes to their eyes on return. More than half. Not a small subset. Not extreme cases. The majority. Some return with permanently altered vision, needing glasses for the first time in their lives. Some develop scotomas, which are blind spots where portions of the visual field simply go dark. Some show persistent swelling of the optic nerve that does not fully resolve after return to Earth. The damage, in those cases, is not temporary. Now carry that forward to Mars. The gravity reduction on Mars is less severe than in orbit. The fluid accumulation would be less acute. But a colonist on Mars is not there for 6 months. They are there for life. The exposure is chronic, measured not in mission duration, but in decades. And the population exposed includes precision technicians, engineers, surgeons, pilots, everyone on whom the colony's survival depends. Progressive visual impairment is not a medical complication in that context. It is a slow erosion of the colony's ability to function. That is the third piece of the gravity line of evidence. Bone, marrow, muscle, heart, vestibular system, vision, 6 systems, each degraded by the same missing signal. And this is the moment to step back and look at all of them at once. These failures do not add up. They multiply. Consider the chain. Bone loss reduces the marrow space inside bone. Reduced marrow space lowers production of red blood cells, white blood cells, and platelets. Lower red blood cell counts reduce the oxygen available to muscle. Lower white blood cell counts impair immune response, which means infections last longer and hit harder. Lower platelet counts slow healing. Slower healing makes every injury more dangerous. A colonist who is more frequently ill, more slowly healing, and more at risk from injury naturally reduces physical activity. Reduced activity lowers the mechanical load on muscle. Lower load means faster muscle loss. Less muscle mass lowers cardiovascular fitness, because the heart and lungs are trained by the demand the muscles place on them. Lower cardiovascular fitness reduces exercise tolerance, and reduced exercise tolerance drives further bone and muscle loss because the body receives even less of the loading signal that tells it to maintain what it has. Each failure loads the others. The structure is not a list of separate problems. It is a set of members where each one depends on the others, and each one weakening increases the stress on what remains. Remove enough of them, and the load is not distributed. It falls. This is what the word colonist obscures. The word suggests individuals making choices, managing health, adapting to a new environment. The biology suggests a cascade, a slow, self-reinforcing decline that accelerates as it goes, and that no individual intervention fully interrupts because the interventions are themselves dependent on the system's declining. Wait, because there is a critical distinction that has been implied, but not stated directly. Every piece of evidence so far has described adults who grew up on Earth, who developed their skeletons under Earth gravity, who trained their hearts and muscles against Earth's full pull, who calibrated their vestibular systems to Earth's constant signal. The question so far has been whether those adults can survive on Mars. The answer, cautiously, is probably yes. For a time. For decades, perhaps. With medical support and discipline and engineering, adult bodies are robust enough to endure partial gravity for a long while before the cascade reaches a critical threshold. That is not nothing. But permanent settlement is not a question about the founders. It is a question about their children, and their children's children. It is a question about humans who will never experience Earth gravity at all, who will develop from conception, through birth, through infancy, through adolescence, entirely inside a 38% gravitational field, whose bones will form under that load, whose hearts will develop against that demand, whose vestibular systems will calibrate to that signal, and nothing else. Everything covered so far has been about what gravity does to an adult body when you take gravity away. The harder question is what happens when gravity was never there at all, and the gravity thread is only the first of three. The second reaches somewhere most people would not expect it to. Not into the musculoskeletal system, not into cardiovascular function, into the cell itself, and into everything that happens before a child is born. Before radiation reaches a human body on Mars, it passes through nothing. No field, no ocean of air, nothing at all. That is the second thread. And it begins not with Mars, but with what surrounds us here, invisibly, every moment of every day. Most people have never thought about what stands between them and the radiation coming from the sun, from dying stars, from sources billions of light years away. The answer is two things: stacked. And most people have never thought about either one, because neither one announces itself. They simply work. The first is the magnetic field. Earth generates it deep inside the planet, where a liquid iron outer core rotates and convects, driving in effect something like a massive electrical generator. That generator produces a magnetosphere, a vast invisible field that extends tens of thousands of miles out into space in every direction. What the magnetosphere does, continuously, is deflect. Charged particles streaming from the sun, cosmic rays accelerated by distant supernovae, high-energy radiation from across the galaxy. The field bends them away, it turns them aside. Roughly 99% of the harmful radiation that approaches Earth never reaches the surface at all. The particles that do get through are funneled toward the poles, channeled along magnetic field lines into the upper atmosphere. We can see the result of this process on clear nights at high latitudes. The aurora borealis, those slow green and violet curtains of light, is the visible signature of the shield doing its job. Every time the aurora appears, that is what it means. The magnetosphere caught radiation and sent it somewhere harmless. The second shield is the atmosphere. People think of the atmosphere as air to breathe. That picture is incomplete. The atmosphere is, by mass, roughly 5 quadrillion tons of gas pressing down from above and in from every side. It is an ocean, and we live at the bottom of it. That mass provides radiation shielding equivalent to roughly 3 feet of solid aluminum wrapped around the entire planet in every direction. Not 3 feet above you. 3 feet in every direction, always present, in the form of air. The two shields together create a radiation environment at Earth's surface that is, in evolutionary terms, the only radiation environment the human genome has ever known. Our DNA repair systems are calibrated to it. Our reproductive cells evolved inside it. Embryonic development, from the first cell division onward, proceeds against the background radiation that these two shields allow through and no more. The body is not built to handle less damage or more. It is built to handle exactly this much. Now consider what Mars offers. Mars lost its global magnetic field approximately 4 billion years ago. The mechanism is the same one that generates Earth's field, run in reverse. Mars has a smaller core. It cooled faster. The liquid iron outer core that drives the dynamo effect solidified, and when it did, the planetary magnetic field collapsed. What remains are localized crustal anomalies, patches where the ancient field is frozen into Martian rock like a fossil, still pointing in the direction it was pointing billions of years ago. These remnants offer minimal protection over small patches of surface. They are archaeological evidence of a shield, not a shield. And the atmosphere? Mars's atmospheric pressure at the surface is approximately 6 millibars. Earth's is approximately 1,000. Mars has less than 1% of Earth's atmospheric density. The thin layer of carbon dioxide that clings to the Martian surface provides negligible radiation shielding. Not reduced shielding, not partial shielding. Negligible. It is the difference between standing at the bottom of an ocean and standing in almost nothing at all. A body on the Martian surface is exposed. Not partly exposed. Not exposed in ways that can be casually managed. Fully exposed, continuously, in a way that has no equivalent in the environment our biology was built for. But the reality was different. We are not speculating about this exposure. We have measured it. The Curiosity rover carries an instrument called the Radiation Assessment Detector. It has been recording radiation levels on the Martian surface since the rover landed. The numbers it returns are exact, not modeled, not estimated from theory, measured, on the ground, by an instrument built for this purpose. The Martian surface dose runs approximately 240 microsieverts per day. A microsievert is a unit of radiation dose, specifically the dose adjusted for biological effect on human tissue. The number itself requires context. Earth's natural background radiation runs approximately 2,400 microsieverts per year. That works out to roughly 6 or 7 microsieverts per day, averaged across a year at the surface, protected by the full weight of the magnetic field and the atmospheric ocean above. The Martian surface delivers 240 per day. Earth delivers 6 or 7 per day. That ratio deserves to sit for a moment. A single day on the Martian surface delivers roughly what Earth delivers in 10. Not in a week, not in a bad week. In 10 days. Daily Mars exposure runs 35 to 40 times Earth's typical daily background. Annual exposure on the Martian surface reaches approximately 90,000 microsieverts, which is 90 millisieverts, which is nearly 40 times Earth's annual natural background. This is not a number that falls inside the range human DNA repair systems evolved to manage. It falls far outside it. The repair mechanisms that catch and correct radiation-induced DNA damage are calibrated to the Earth environment. They handle a certain volume of damage per day, per year, across a lifetime. They have never been calibrated by any selection pressure across any evolutionary time for 40 times that volume. What matters for permanent settlement is not the single-year dose. It is the cumulative dose across a lifetime, and it is the dose received by reproductive cells, and it is the dose received by developing embryos and infants and children whose cells are dividing rapidly, whose tissues are forming, whose genomes are being assembled into the architecture of a complete human body. The radiation thread compounds the gravity thread. Every biological system already being stressed by reduced load is simultaneously being bathed in a radiation environment that exceeds what it was built to handle. These are not two separate problems progressing in parallel. They share the same body, they press on the same cells, they challenge the same repair machinery, and radiation is only the second thread. The third has not arrived yet. That number, 90 millisieverts per year, invites an obvious question. If the dose is that high, why not simply build thicker walls? Why not engineer a habitat with shielding substantial enough to bring the radiation down to a level the body can manage? The answer is not a matter of engineering effort, the answer is physics. And the physics, when you look at it closely, does not cooperate in the way common sense suggests it should. The first thing to understand is that there are two distinct kinds of radiation reaching the Martian surface. They come from different places, they carry different particles, they cause different kinds of damage, and they respond very differently to the idea of a wall. The first kind is solar particle events. These are bursts of charged particles, mostly protons, released by solar flares and coronal mass ejections from the sun. They also carry electrons and some heavier ions. The energy per particle is relatively modest by cosmic standards. More importantly, they can be predicted. Space weather satellites watch the sun continuously. When a flare erupts, hours of warning arrive before the particles reach Mars. A shelter with modest shielding, water tanks, polyethylene lining, packed Martian regolith can reduce the dose from a solar particle event to manageable levels. Engineering can address solar particle events. Barely, but it can. The second kind is galactic cosmic rays. This is where the physics stops being cooperative. Galactic cosmic rays do not come from the sun. They originate from supernovae, neutron star collisions, and other extreme galactic events. They have traveled millions of years across interstellar space before arriving at Mars. They travel at near light speed, and they cannot be predicted because they arrive continuously from every direction at all times, regardless of what the sun is doing. Their composition looks like this. About 87% are protons, about 12% are helium nuclei, about 1% are heavier nuclei, particles made of carbon, oxygen, silicon, and iron. That 1% is the problem, not the majority, the minority. A single iron nucleus traveling at roughly 90% of the speed of light carries kinetic energy comparable to a fast-pitched baseball, concentrated in a particle smaller than a trillionth of a millimeter. The disproportion between the scale of the energy and the scale of the particle is almost impossible to hold in mind. The energy is real, the particle is invisible, and when that iron nucleus passes through living tissue, it does not simply deposit energy the way an X-ray does. It tears a path. Here is the mechanism. As the heavy ion moves through tissue, it strips electrons from atoms along its entire trajectory. It ionizes thousands of atoms in a straight cylinder, punching through multiple cells in sequence. If the path passes through a cell nucleus, it does not produce a single strand break, the kind of damage that DNA repair machinery handles routinely. It produces clustered damage. Both strands of the DNA double helix break in the same location. Multiple nearby modifications occur simultaneously. The repair systems that catch and fix individual errors are not built for this. They can address isolated damage. They cannot address a site where the DNA has been shattered in multiple overlapping ways at once. When repair is attempted, it introduces errors. Chromosomes rejoin incorrectly. Oncogenes can activate. Tumor suppressors can be switched off. The biological effectiveness of heavy ion radiation is 20 to 40 times greater than gamma rays or X-rays for the same physical dose. That multiplier changes everything, because it means that 90 millisieverts per year of galactic cosmic ray exposure is not the same as 90 millisieverts of medical X-ray exposure. It is biologically equivalent to several hundred millisieverts of X-ray exposure. The number on paper understates the biological weight of what is actually happening inside the tissue. So the next question is, can a wall stop it? Here is where it gets strange. An iron nucleus at 90% of the speed of light can pass through several feet of solid aluminum before stopping. No practical habitat wall can be made thick enough to halt it entirely. But the failure of thick walls is not simply a matter of the particle passing through. The failure is more counterintuitive than that. When galactic cosmic rays strike shielding material, they do not simply lose energy and stop. They shatter the nuclei of the atoms in the shield. That shattering produces secondary radiation cascades, fragments, neutrons, protons, pions, and nuclear debris that scatter inward from the point of impact. A wall struck hard enough does not absorb the threat. It breaks into pieces that propagate the threat in a new form. For some materials and some thicknesses, the dose inside the shielded space actually exceeds the dose in an unshielded space. More shielding produces more exposure. The wall is generating its own radiation. Not all materials behave equally badly. Hydrogen-rich materials, polyethylene and water, perform significantly better than aluminum or steel. The reason is mass matching. Hydrogen nuclei are close in mass to neutrons. When a neutron strikes a hydrogen nucleus, it transfers energy efficiently, the way two billiard balls of equal mass transfer momentum cleanly. The neutron slows. The secondary cascade is suppressed. Optimized hydrogen-rich shielding is the best available option. But even optimized hydrogen-rich shielding achieves only about 50% reduction in galactic cosmic ray dose. Underground habitats seem like the obvious answer. Meters of Martian regolith above a habitat should provide substantial protection. And against solar particle events, they do. But against galactic cosmic rays, the regolith behaves the way any shielding material behaves when struck by near light speed, heavy ions. It produces secondary cascades. Neutrons are generated inside the rock and propagate downward. Detailed simulations suggest roughly 50% reduction in dose underground, consistent with what optimized hydrogen-rich shielding achieves above ground. The floor is not zero. The floor is not close to zero. Even with optimal shielding, either hydrogen-rich materials above ground or several meters of regolith below it, the residual radiation exposure on Mars is approximately 45 millisieverts per year. That is still roughly 20 times Earth's natural background radiation. Every day, every year, for life. Not for a mission duration, not for a calculated career limit. For life, from childhood through old age, with no reduction and no reprieve, because the physics of what galactic cosmic rays are and how they interact with matter does not offer one. This is the floor that engineering has reached. Active magnetic shielding, the idea of generating an artificial magnetic field around a habitat to deflect incoming particles, the way Earth's magnetosphere does for the planet, remains theoretically possible and practically unsolved at any scale relevant to a colony. No current design comes close to deployment. The shielding problem as it stands today leaves every Mars colonist exposed to radiation 20 times Earth's background for as long as they live there. And the radiation thread, as heavy as it is still only the second thread. The third has not arrived yet. Live inside that dose for decades, and here is what happens to a single person. The radiation does not arrive as a single event. It does not deliver one large injury that the body absorbs and recovers from. It arrives as a continuous accumulation, day after day, year after year, working on the same biological architecture in two distinct and simultaneous ways. The first way is direct. When a high-energy particle passes through tissue, it can strip electrons directly from the atoms that make up a DNA molecule. Stripped electrons mean broken chemical bonds. Broken bonds mean the helix can fragment. A strand can snap. A base can be modified into a form the cell cannot read correctly. The damage is structural, immediate, and physical. The second way is indirect, and it reaches farther. Human cells are roughly 70% water. When radiation passes through that water, it can ionize the water molecules themselves, knocking electrons loose and producing what chemists call reactive oxygen species. These are highly unstable molecular fragments that tear through cellular chemistry, attacking DNA hundreds of nanometers away from where the original ionization happened. The particle passes through. The chemistry continues afterward. Both pathways produce the same categories of damage: strand breaks, modified bases, and crosslinks where two parts of the molecule become fused in ways that lock or corrupt the sequence. And this is where something important needs to be understood. The body already weathers this kind of damage on Earth. Metabolism, background radiation, and ordinary cellular chemistry produce tens of thousands of DNA damage events in each cell, every day. The repair systems that handle this are ancient, sophisticated, and genuinely effective. Single-strand breaks are repaired accurately because the intact complementary strand serves as a template. The cell reads the undamaged side and reconstructs what was lost. Double-strand breaks are a different problem. When both strands snap at nearly the same location, there is no intact template. Repair machinery must rejoin the broken ends without a guide, and the error rate is higher. On Earth, this happens rarely enough that natural selection, across generations, has kept the accumulated load of errors manageable. Most cells repair correctly. Some don't, and those accumulate mutations slowly, over decades, against the backdrop of a radiation environment that human biology has had 4 billion years to accommodate. Mars changes the ratio. Under 45 millisieverts of unavoidable annual exposure, damage outpaces repair. Not dramatically at first, incrementally, year after year. Repair systems make more errors under heavier load. Mutations accumulate faster than selection pressure can clear them. And those accumulated mutations have a statistical relationship with cancer that researchers have spent decades measuring with precision. The model comes from 3 populations studied over many decades: atomic bomb survivors in Japan, nuclear industry workers with documented occupational exposure, and medical radiation patients. Across all 3 groups, the relationship is consistent. Every 100 millisieverts of cumulative radiation exposure raises lifetime cancer risk by approximately 0.5 percentage points. That is the linear no-threshold model. It has been contested at the margins, debated in its application to very low doses, but for doses in the range that Mars colonists would accumulate, it represents the best established quantitative tool available. Apply it to Mars. At 45 millisieverts per year under optimal shielding conditions, a Mars colonist adds roughly 0.5 percentage points to their lifetime cancer risk every year of residence. After 10 years, plus 5 percentage points. After 20 years, plus 10. After 30 years, plus 15. The baseline lifetime cancer risk for humans on Earth is approximately 40%. Not a small number, even before any additional exposure. A 30-year Mars resident reaches roughly 55%. More than half. That is not the tail risk. That is not the statistical outcome reserved for the unlucky minority. That is the majority outcome for anyone who lives on Mars for 3 decades. Cancer becomes the expected result, not the exceptional one. Every year of residence tips the balance a fixed increment further. There is no plateau. There is no dose at which the body stops accumulating risk. The scale tilts by the same amount each year, and it only tilts in one direction. That is the cancer story. But radiation does a second thing to the human body that runs in parallel, through a completely different mechanism, and in some ways the outcome is harder to recover from. Neurons do not divide. Most cells in the body can replace damaged neighbors. Skin cells, immune cells, gut lining cells, blood cells, all of them turn over, replicate, and replenish the population. When radiation kills or damages them, the tissue regenerates. The loss is temporary. Neurons cannot do this. The brain cells that fire signals, hold memories, and coordinate decision-making are largely the cells you were born with. Radiation that kills or permanently damages a neuron leaves a vacancy that nothing fills. Think of a city where every building, once destroyed, is gone permanently. No construction crews come. No rebuilding happens. The skyline simply becomes less dense, one structure at a time. The brain's defense against this is redundancy. Neural circuits have more capacity than daily tasks require. A modest number of lost neurons produces no measurable effect, because the remaining network compensates. But redundancy has limits. Progressive neuron loss from chronic radiation exposure eventually crosses those limits. What emerges is not a dramatic event. It is a slow gradient. Processing speed declines, working memory degrades, executive function, the capacity to hold complex plans and adapt them under pressure, becomes less precise. Studies of astronauts returning from long-duration missions already show this. Measurable, persistent changes in processing speed, working memory, and attention have been documented in people who spent months in orbit. These are not temporary effects that resolve after readjustment. Some persist. Some show no clear recovery trajectory at all. On Mars, the exposure is not a 6-month mission, followed by a return to Earth and a lower radiation environment. It is continuous, from arrival through the end of life, with no interruption and no recovery window. Progressive cognitive decline begins early and accumulates across decades. Here is what makes this more than a personal medical outcome. The colonists facing this cognitive erosion are the same people responsible for maintaining the life support systems the colony depends on: the air recycling, the water purification, the pressure regulation, the food production, the systems that fail catastrophically if not understood, monitored, and maintained correctly. A colony populated by people whose cognitive processing is declining under chronic radiation is a colony with a narrowing margin for error. The two curves, the one for radiation exposure and the one for colony complexity, run in opposite directions. Something else was happening. The adults, the founders who arrived already fully developed, face the worst of this slowly. Their nervous systems are complete. Their bones are formed. Their cardiovascular systems are calibrated. The damage accumulates from an established baseline. Children who are born on Mars, or who arrive young enough to develop there, face a different equation entirely. Developing brains are not simply smaller adult brains. They are brains in the process of constructing their own architecture, regions growing, connections forming, pruning occurring on a tightly regulated schedule. A developing brain exposed to chronic radiation is not losing cells from a completed structure. It is trying to build a structure while the building materials are being damaged and the blueprints are being corrupted. Children's developing brains are several times more vulnerable per unit dose than adult brains, and fetuses are the most vulnerable of all. The cancer math and the cognitive decline together describe what a single lifetime on Mars looks like. A 55% probability of cancer over 3 decades of residence. A progressive, irreversible erosion of the cognitive capacity the colony needs to function. And a developmental vulnerability in every child and every fetus that multiplies the effect across generations. That last part is where the argument goes next. Step back from any single lifetime. Step back from the cancer accumulating in one person's cells, from the neurons fading in one person's brain, from the fetus developing under chronic radiation in one person's body. Step back further. What you see across the line of generations is something different, something the individual never feels but every generation inherits. The human genome contains roughly 3 billion base pairs. The full instruction set for building and running a human body, written in a molecular alphabet, 4 letters long. Every time a reproductive cell is formed, that instruction set is copied, and every copy contains errors. On Earth, the rate of new mutations per genome per generation sits at roughly 70 to 100. 70 to 100 new changes in a sequence 3 billion letters long. Most fall in regions that don't code for anything critical. Many that do fall in genes are neutral. Only a small fraction affect fitness in ways that matter. The balance between new mutations entering the gene pool and natural selection removing the harmful ones has been stable across evolutionary time. It has been stable because the radiation environment that shapes that balance has been stable. Earth's background radiation has not changed meaningfully in the time our species has existed. The mutation rate and the selection rate have reached a kind of equilibrium. Mars breaks that equilibrium. Under the best available shielding, a Mars colonist absorbs roughly 45 millisieverts of radiation per year. And radiation damage does not stop at the body's somatic cells, the skin and gut and blood. It reaches the reproductive cells. It reaches the eggs and the sperm. When it does, mutations in those cells are not just health events for one person. They become inheritance events for every subsequent generation. The mathematics is unforgiving. Elevated radiation could push the count of new mutations per genome per generation to several hundred, or under high parental exposure, to thousands. That number is not a minor statistical shift. It is a structural change in the relationship between new damage entering the gene pool and the rate at which selection can remove it. Selection works slowly. It operates across generations, across many offspring, across differential survival and reproduction. When harmful mutations arrive faster than selection can purge them, they accumulate. Each generation inherits the parent's load, plus its own new damage. The load grows. This is what population geneticists call mutational load. Not a poetic term, a technical one. The total burden of mildly harmful variants a population carries. Think of it as a vessel taking on water faster than it can be bailed. The vessel does not sink immediately, but the waterline rises. Generation by generation, it rises. And fitness, the aggregate capacity to survive and reproduce successfully, falls with it. The models are explicit about what that trajectory looks like. Within 3 to 5 generations, the projections converge on the same pattern. Fertility falls, pregnancy success rates decline, miscarriage rates rise, driven by chromosomally abnormal embryos that cannot complete development. Infant mortality rises, driven by developmental abnormalities that were not survivable. The colony begins to struggle to maintain replacement reproduction, not because of any single dramatic failure, because the waterline has been rising since the first generation, and the margin has been narrowing with it. Within 7 to 10 generations, the models agree on a darker picture. Genetic disease frequencies climb across the population. Average lifespan falls. Cognitive capacity declines as mutations accumulate in the genes governing neural development. And the colony begins to lose the capacity to maintain its own technology. The people responsible for keeping the life support systems running are the same people whose gene pools have been degrading since the settlement began. The technical complexity the colony requires does not decrease as the generations pass. The cognitive capacity available to meet it does. The models differ on exact timing. They depend on assumed shielding effectiveness, population size, selection intensity, but they do not differ on direction. The direction is certain. The answer was stranger than expected. Most people, when they think about radiation risk on Mars, think about cancer. They think about individual health outcomes, about one colonist's elevated probability of developing a tumor. That framing is not wrong, but it is incomplete. The more devastating consequence operates at a different level entirely. It operates on the gene pool, across generations, invisibly, irreversibly, on a timescale that no individual ever fully perceives. No colonist in the first generation will look around and see a collapsing population. No colonist in the third generation will feel the mutational load accumulating in their genome. The damage is real. The trajectory is already set. The consequences arrive on a schedule measured in lifetimes, not in days. There is a second mechanism working alongside this one, separate from inherited mutation, separate from the gene pool accumulating damage across generations. It operates inside the body's own reproductive hardware, in the cells that make reproduction possible. Women are born with their lifetime supply of eggs already formed. No new eggs are generated after birth. Every egg a woman carries has been present since before she drew her first breath. That means radiation damage to eggs accumulates across the entire lifespan, with no mechanism for replacement or repair. A woman who has lived 30 years on Mars carries 30 years of accumulated radiation damage in the very cells she would pass to the next generation. Not just her somatic cells, her eggs, the cells that carry her half of the genetic instruction set. Men face a different but parallel problem. Men do continuously produce new sperm. That sounds like an advantage. But the spermatogenic stem cells, the cells deep in the testes that generate sperm throughout a man's life, are themselves vulnerable to radiation damage. When those stem cells are damaged, every sperm they subsequently produce carries the consequences. Sperm count falls, motility, the ability of sperm to swim effectively, declines. Morphology, The structural integrity of individual sperm cells degrades. Conception becomes harder. And the sperm that do succeed in fertilizing an egg carry more genetic damage than they would have carried on Earth. The combined effect compounds: declining conception rates, rising miscarriage rates, accumulating heritable damage in the embryos that do complete development. This is not the slow generational pressure of mutational load working across centuries. This is a fertility crisis building across decades, driven by direct biological damage to the very structures of reproduction depends on. People working on this problem have proposed solutions. Underground habitats cut radiation exposure significantly against solar particle events. Against galactic cosmic rays, the more penetrating threat, the best underground shielding achieves roughly 50% reduction. The residual exposure remains around 20 times Earth's natural background. The trajectory is slowed, it is not prevented. A few more generations before the waterline reaches the same level. Pharmaceutical radioprotectants, compounds developed partly through military research on radiation exposure, offer some protection. Some enhance the body's own DNA repair mechanisms. Some scavenge the reactive oxygen species that drive indirect radiation damage. Against low-energy radiation, they help modestly. Against heavy ions, the galactic cosmic rays that tear through shielding and biological tissue alike, they provide very little. No drug currently exists that meaningfully protects against direct ionization by the particles that carry the greatest mutagenic load. Then, there is the idea that sits at the furthest edge of the proposed solutions: genetic engineering, borrowing radiation resistance from organisms that already have it. The bacterium Deinococcus radiodurans survives radiation doses thousands of times the human lethal dose. Tardigrades, the microscopic animals sometimes called water bears, can enter a cryptobiotic state, a kind of suspended biological animation that allows them to survive conditions that would kill virtually any other life on Earth, including extreme radiation. Their mechanisms are real: enhanced DNA repair pathways, redundant copies of the genome, unique DNA-binding proteins that prevent radiation from fragmenting chromosomes, powerful free radical scavenging systems that neutralize reactive oxygen species before they can attack DNA. These are not metaphors. They are functional biological machinery. In principle, the argument goes, those mechanisms could be introduced into humans. In principle. But here is what principle leaves out. Importing those mechanisms would mean redesigning core human cellular machinery, the existing DNA repair systems, the protein networks that govern how chromosomes are organized and accessed, the metabolic pathways that balance free radical production against antioxidant capacity. These are not modular components that can be upgraded in isolation. They are deeply integrated with thousands of other cellular processes, the product of billions of years of evolutionary refinement. Introducing Deinococcus-style DNA repair into a human cell would not be like installing a better immune system. It would mean producing something whose fundamental cellular biology no longer operates on human terms. Not a modified human, not an enhanced human, something else. And even setting that aside entirely, even imagining a future in which the technical and ethical problems were somehow resolved, a modification that only partially reduces excess mutations would only delay the collapse, not prevent it. The waterline would still rise, more slowly perhaps, but rising. What remains underneath all of it is a biological reality that partial solutions can soften, but cannot erase. The mutation rate rises. The selection pressure does not rise with it. The gene pool accumulates damage it cannot shed. And the reproductive organs that would carry the next generation forward are absorbing that same radiation across the same lifetimes without repair. The trajectory is not a worst-case projection. It is the direction every model points. Regardless of assumptions, regardless of the exact timing, regardless of how optimistic the shielding parameters are set, that direction has consequences for every other argument about long-term Mars habitation. And there is one more thread that has not yet arrived. Set radiation aside completely. Not as a concession, not as a rhetorical move, as a genuine thought experiment. Suppose the radiation problem did not exist. Suppose every dose, every heavy ion, every reactive oxygen species fragmenting a strand of DNA were somehow removed from the equation. What would remain? What would remain is this: a body still has to be built. And building a body is not a process that happens in a void. It happens in gravity. It has always happened in gravity. Every embryo, every organism, every multicellular life form that has ever existed on this planet developed inside the same gravitational field, at the same 9.8 meters per second squared, without exception and without variation, for the entire history of life on Earth. Gravity is not a background condition of development. It is an input, a required input, one that developmental biology has never had to function without. An embryo begins as something smaller than a grain of salt. That object contains the complete instruction set for building a human being. But the instructions do not operate in isolation. They operate in an environment. They assume specific physical conditions. They assume chemical gradients that form correctly in a field that tells molecules which direction is down. They assume mechanical forces that propagate through tissues in predictable directions. They assume, at the most fundamental level, that gravity is present and constant. Because for every ancestor of every living human, it always was. Gravity is the invisible scaffold against which every embryo has organized its growth since the first multicellular organisms emerged from ancient seas. Change the scaffold, and what builds itself against it changes too. That is when the pattern broke. The earliest experimental results did not suggest a problem. Rodent reproduction experiments began on space shuttle missions in the 1980s and continued aboard the International Space Station. Researchers tested fertilization first. Sperm swam normally. Eggs could be penetrated. Gamete fusion succeeded. The initial finding was encouraging. It suggested that the fundamental act of conception was not disrupted by microgravity. Some researchers took this as early evidence that space reproduction might be feasible. It was not. Fertilization is a single event. Development is thousands of sequential events, each depending on the last, each assuming the same physical environment that shaped the one before it. And when researchers examined what happened after fertilization, the picture changed completely. Cell division rates changed, but more critically, the normal asymmetric distribution of cellular components during division failed. This requires a brief explanation because it is the foundation of everything that follows. Early cells in an embryo are not supposed to be equivalent. During the first divisions, some cells should inherit more cytoplasm. Some should inherit specific molecular signals. These differences are not random. They are the mechanism by which cells acquire different identities. The cells that receive certain signals become the inner cell mass, which is the embryo proper. The cells that receive others become the trophoblast, which is the tissue that forms the placenta. The distinction between these populations is made in the very first divisions, and gravity plays a role in establishing the orientation that makes it possible. In microgravity, that asymmetry breaks down. The populations fail to separate correctly. The result is not a minor variation. It is a fundamental organizational defect, present from the very beginning of development, before any organ has begun to form. Implantation compounds it. When an embryo reaches the uterine wall, it must attach at the correct angle, with the correct cell populations facing the correct direction. Gravity provides orientation cues that guide this process. In reduced gravity, attachment rates drop, and embryos that do attach often attach abnormally, with cell populations positioned incorrectly relative to the uterine tissue. The placenta, which must then form to exchange oxygen, nutrients and waste between mother and fetus, depends on blood vessel patterns shaped by mechanical forces from blood flow. Blood flow, in turn, depends on gravity. In reduced gravity, the placenta forms with fewer vessels and abnormal architecture. The fetus receives inadequate nutrition, it receives inadequate oxygen. The life support structure for the entire pregnancy is compromised by the same physical condition that compromised the first cell division. And this is where the Mars fraction becomes critically important. Mars' gravity is not zero, it is 38% of Earth's. And there is a temptation, when hearing that number, to treat 38% as a reasonable partial solution. More than a third. Enough to provide meaningful loading. enough to be substantially better than nothing. Developmental biology does not work on those terms. Development runs on tight tolerances, not approximate tolerances, not ranges wide enough to accommodate a 62% reduction in gravitational input. The processes involved are calibrated to a specific mechanical environment. The question is not whether 38% is better than zero. The question is whether 38% is enough. There is no evidence that it is. There is substantial evidence that it is not. Bones make this concrete. Bones form through a process called endochondral ossification. A cartilage template is laid down first, establishing the shape of the future bone. Then that template is mineralized, gradually replaced by hard bone tissue. The process requires a mechanical loading to proceed correctly. Cartilage templates need the signals that come from weight bearing and muscle pull, and the physical stress of a body moving against gravity. Without those signals, the templates form abnormally, smaller, differently shaped. In reduced gravity, ossification centers appear later than they should. They spread more slowly. The bones that result are smaller than they should be, less dense than they should be, and architecturally wrong in ways that cannot be corrected after the fact. These are not bones that happen to be slightly weaker. They are bones built to a different specification than any human skeleton in evolutionary history. A child who develops on Mars would have bones unlike any that have existed before. Bones that might fracture from normal childhood play. Bones whose growth plates function abnormally, impairing further growth. And bones whose architecture reflects the gravity that built them, not the gravity of Earth, and not the gravity of any ancestor. The skull specifically forms by two roots. The cranial base develops through endochondral ossification, the same process as the long bones. The cranial vault, the dome that protects the brain, develops through a different process called intramembranous ossification, where bone forms directly from connective tissue without a cartilage intermediate. Both processes are sensitive to mechanical force. A Mars-developed skull could be thinner and less protective than any human skull on record. A minor fall, the kind of fall any child takes on any ordinary afternoon, could produce head injuries that compound neural damage already accumulating from other causes. The heart follows the same logic, beginning even earlier. Around day 22 of development, the fetal heart begins to beat. At that point, it is not yet the four-chambered structure that will sustain a human life. It is a simple tube. Over the following weeks, it transforms through a sequence of folding, looping, and division, a process called septation, into the organ it must become. Blood flowing through the developing heart provides shear stress signals along the inner walls. Those mechanical signals guide the further development of the chambers. They tell the walls how thick to grow. They tell the valves how to form. They calibrate the entire architecture of the finished heart to the circulatory demands of the gravity field it is developing inside. In altered gravity, blood flow patterns change. The shear stress signals the developing heart receives are different. The heart wires itself to those signals, and only to those signals. The result is a heart whose chambers are proportioned for a non-Earth circulation, whose walls are calibrated for pressures that Earth gravity would never impose. A heart that was constructed by a body that expected to live its entire life in 38% gravity, because that was all it had ever known. Such a heart would not handle Earth gravity if the child were ever transported there. But even on Mars, it would carry a deficit. A heart with wrong proportions and walls calibrated for wrong pressures lacks the reserve capacity to handle stress, infection, or the additional demands of growth. Not at rest, perhaps. Not in ordinary daily life on a quiet morning in a stable habitat. But at the margins, where biological reserve matters most, it would fall short. What is emerging here is not a single system failing. It is a sequence of failures, each arising from the same cause, each compounding the others. An embryo whose cells failed to organize correctly. A placenta that delivered inadequate nutrition to a developing fetus. Bones built to a wrong specification. A cardiovascular system wired to a non-Earth circulation. Each defect arriving before the child is born, and each one carrying consequences the others cannot compensate for. And skeletal and cardiovascular development are only the beginning of what gravity shapes. Two systems remain in that developing child, and both of them shape who that child will be in ways that will never be corrected after the fact. The vestibular organs begin forming in the 4th week of development. These are the structures buried deep in the inner ear that sense gravity, acceleration, and the orientation of the head in space. They are not simple sensors. They calibrate. They adjust themselves to whatever gravitational environment they experience during development. And then, they lock that calibration in. On Earth, that calibration is always the same. Every human vestibular system in history has tuned itself to 9.8 meters per second squared. The system works because the reference point never changes. On Mars, the reference point is 38% of that. A child whose vestibular organs develop inside a 38% gravity field calibrates to 38% gravity. Not as a compromise, not as a temporary adjustment, as the baseline, the correct value, the one against which every downstream signal is measured. And that miscalibration does not stay in the inner ear. It propagates outward, into vision, into balance, into motor control, into spatial cognition. The brain integrates vestibular signals with visual information thousands of times per second, constructing a continuous model of where the body is in space. When the vestibular reference is wrong, the model is wrong, not occasionally, continuously. But the picture did not hold. The vestibular problem is not just a calibration problem, it is a construction problem. During fetal brain development, neurons migrate. They travel from where they are produced to where they are supposed to settle, following molecular signals and mechanical cues. Gravity is one of those cues. The pattern of fluid pressure inside the developing skull, the mechanical loading on developing neural tissue, the distribution of forces across the growing brain, all of it is influenced by gravity. In altered gravity, neurons end up in the wrong locations. Not dramatically wrong, not in ways that would be visible on casual observation, but wrong in their final positions relative to the circuits they are supposed to form. Synaptic connections form between neurons based on proximity and molecular matching. When neurons are displaced, the circuits they form are different. The synaptic density across certain regions is altered. The vestibulo-cerebellar connections are particularly vulnerable. These are the pathways linking the vestibular organs to the cerebellum, the region of the brain responsible for balance, motor coordination, and motor learning. A Mars-developed brain would build these pathways against a 38% gravity signal, calibrated from the wrong reference, routed through neurons that migrate to slightly wrong positions. The resulting architecture is not a damaged Earth brain. It is a different brain, functional, perhaps, in the environment that shaped it, but different from every human brain that has existed across the entire span of evolutionary history. In routine daily life on Mars, that difference might go largely unnoticed. Simple motor tasks, ordinary conversation, basic navigation of a habitat. A Mars-born child might appear, to casual observation, unremarkable. The difference would emerge in complex tasks. Tasks combining spatial reasoning with abstract integration. Tasks requiring the kind of rapid, flexible recalibration that Earth-developed neural architecture performs without effort. There, the difference would surface. And in a colony, depending on its inhabitants to operate intricate life support systems, to troubleshoot equipment failures, to manage the compounding cognitive demands of an isolated and technically complex environment, that difference would matter. The immune system compounds everything that comes before it. T cells are the coordinators of the adaptive immune response. They identify specific threats, direct other immune cells toward targets, and carry the molecular memory that allows the immune system to respond more rapidly to infections it has seen before. T cells do not develop in the blood. They develop in the thymus, a small organ behind the sternum, through a selection process that shapes which T cells survive and what they are capable of recognizing. That selection process requires mechanical interaction. Developing T cells physically contact thymic epithelial cells, the structural cells lining the thymus, and those contacts determine which T cells pass selection and which are eliminated. The geometry of those contacts, the physical forces involved, the mechanical environment of the thymus during development, all of this is sensitive to gravity. In altered gravity, the selection process is disrupted. The resulting immune repertoire is abnormal. Different proportions of T-cell populations, different functional capabilities, a different distribution of what the immune system can and cannot recognize. And unlike many developmental defects, this one does not correct itself if the environment later changes. The immune repertoire a person carries through life is largely set during development. Return a Mars-born child to Earth gravity, and the immune system does not rebuild itself. What was built under abnormal conditions remains. The deficiency is not transient, it is permanent. For children developing on Mars, this means specific immune cell populations are absent or underrepresented. The populations that are present are functionally impaired. Infections that an Earth-developed immune system handles without crisis become serious threats. Respiratory infections, gastrointestinal pathogens, the ordinary microbial challenges of living in close quarters with other people. In a closed habitat, sharing recirculated air and water, those challenges will arrive constantly, and the immune systems facing them will be inadequate for the task, not weakened, fundamentally differently built. Now consider that child as a whole, bones built to a wrong specification, a cardiovascular system calibrated for pressures and flows that do not match Earth, and that carry insufficient reserve even for Mars under stress, a brain with the vestibulocerebellar circuits constructed from a wrong gravity reference, with neurons settled in subtly wrong positions, forming subtly wrong circuits, and an immune system shaped by a disrupted selection process into a repertoire that cannot mount the responses that environment will demand of it. Each of these defects is serious on its own. Together they do something worse than add. Organ systems are not independent. They support each other. The cardiovascular system delivers oxygen to the brain. The immune system protects the organs. Skeletal structure shapes how the cardiovascular system distributes blood. When one system is abnormal, it places additional load on the others. When none of the systems is normal, there are no compensating reserves anywhere in the body. Every demand on one system is a demand on all of them, simultaneously, with nothing held in reserve. That is the first generation. Now follow the line forward. The minority of those Mars-born children who survive infancy and childhood and reach reproductive maturity carry all of these injuries into adulthood. Smaller, less dense skeletons, cardiovascular systems with a reduced reserve, cognitively different neural architectures, permanently altered immune repertoires. These are the bodies that will gestate the second generation. And this is where a quiet hope fails. One might expect that the second generation would adapt, that children born inside Mars normal bodies would simply develop as Mars normal, stabilizing at whatever the new baseline is. Not better than Earth humans perhaps, but no worse than the first generation. An accommodation to conditions. That is not what happens. The uterus of a first-generation Mars-born woman developed in 38% gravity. Its vascular architecture is abnormal, shaped by the same reduced mechanical loading that shaped every other vascular structure in her body. Uterine blood flow reflects the cardiovascular system she carries, calibrated to Mars conditions, with reduced reserve and wrong proportions. The mechanical environment of her pregnancy differs from any pregnancy in Earth history, because every input, the gravity, the blood flow, the uterine architecture itself, is different. Placental development, already disrupted by reduced gravity, now occurs inside a uterine environment that is itself developmentally abnormal. The placenta that forms is attempting to build an adequate interface between two circulatory systems, both of which developed under conditions outside the range life evolved to handle. The result is not equivalent to the first generation's placental defects. It is worse. The second generation fetus develops in a doubly abnormal environment. The defects compound. Think of a copy made from a copy. Each generation of reproduction introduces new degradation because the template itself is degraded. The third generation develops inside second generation bodies, which are more impaired than the first. The intrauterine environment is more abnormal. The defects compound further. The models that attempt to quantify this trajectory are not optimistic, and they agree with each other on the direction even when they disagree on precise timing. rising infant mortality with each generation, fewer survivors reaching reproductive age, lower fertility among those who do, accelerating developmental degradation across successive cohorts. The projections converge on population collapse within 5 to 8 generations under continuous reduced gravity development. At roughly 25 years per human generation, that is a horizon between 100 and 200 years from the first Mars-born child. The outcome is not a sudden catastrophe. It does not look like a disaster from the inside. It looks like a quiet narrowing, a founding population perhaps numbering in the thousands, their children fewer, their grandchildren fewer still, each generation smaller, more impaired, less capable of the physical and cognitive demands of maintaining the colony that supports them. A slow biological thinning, generation by generation, until reproduction simply stops succeeding. Not with a crisis, with an absence. Fewer births, more losses, fewer reaching the age where any of it matters. The population does not collapse. It diminishes, quietly, across a century of careful, well-intentioned effort in a habitat that is working exactly as designed. And gravity is only one of the 3 threads running through that population. Surely, faced with all of that, engineering has an answer. The biological problems are severe, but human ingenuity has solved severe problems before. And so the proposals exist. Centrifuges to simulate gravity, artificial wombs to replace the mother's body, genetic engineering to rewrite the human developmental program, terraforming to remake Mars itself. Each one sounds, at first, like the exit from the trap. Each one, examined closely, only moves the walls. The centrifuge proposal is the most intuitive. If Mars gravity is the problem, build a structure that rotates fast enough to push outward at Earth strength. A pregnant woman inside that structure would gestate in something close to 1G. The child would develop in the gravity their biology requires. The solution seems obvious, but the physics pushed back. A centrifuge works by spinning. The force it produces is not uniform. It grows stronger the farther you are from the center of rotation, and weaker the closer you get. In a small centrifuge, the difference between head and feet is significant. The head, closer to the center, experiences less force. The feet, farther out, experience more. That gradient does not vanish because you are trying to help. It is physics, built into the geometry. For that gradient to become small enough that a developing fetus wouldn't notice it, the centrifuge would need to be enormous, hundreds of meters in diameter. Not a room, not a habitat module, a structure the scale of a large stadium, rotating steadily, on a planet where the first colonists are trying to keep the air from running out. That is problem 1. Problem 2 arrives immediately after. Pregnancy lasts 9 months. A woman spending 9 months inside a centrifuge is spending 9 months largely isolated from colony life, separated from work, from community, from the daily rhythms of the settlement. That is one person. Scale it up to a colony trying to maintain its population, and that you need continuous occupancy of enormous centrifuge capacity across every reproductive age woman in the colony, across every pregnancy, across every year. The centrifuge solution requires a permanent class of confined pregnant women rotating in a stadium-scale machine while the colony operates around them. That is not a minor logistical detail. That is a civilization structured around a biological limitation it cannot escape. And problem 3 arrives before the child is even born. Development does not stop at birth. Skeletal growth continues into the early 20s. Neural architecture continues developing through adolescence. Cardiovascular calibration tracks through childhood. If the centrifuge provides Earth gravity for gestation, but the child then grows up on Mars, the prenatal benefit evaporates within the first years of postnatal life. To actually protect development, the centrifuge must continue protecting development. The child must remain inside, through infancy, through childhood, through adolescence, into their early 20s. Families split across the centrifuge boundary, parents in the colony, children rotating in the machine, siblings separated by which developmental stage they are in. The centrifuge solution, fully applied, is a colony that raises its children in a separate rotating world from the one the adults inhabit. But even that is not the deepest problem. A child raised inside a centrifuge at Earth gravity through gestation and childhood and adolescence and young adulthood emerges into Mars as a fully Earth-adapted human being. Their skeleton is calibrated to 1G. Their cardiovascular system is built for 1G. Their vestibular system references 1G. And then they step out into 38% gravity, into a colony that cannot sustain Earth gravity outside the machine. That adult now faces everything the founding generation faced. The bone loss, the cardiovascular deconditioning, the same cascade of biological degradation the centrifuge was designed to prevent. Not prevented. Deferred. The centrifuge does not produce Mars-adapted people. It produces Earth-adapted people, marooned on Mars, inheriting every adult consequence that was already documented. Artificial wombs seem to sidestep some of this. If the fetus can gestate outside the mother's body entirely, in a chamber calibrated to Earth normal conditions, then pregnancy itself escapes the centrifuge problem. The developing child would not depend on the mother's gravity-adapted physiology. The gestational environment could be precisely controlled. The technology does not exist at that level. Animal experiments are at early stages. Extending a working system to human gestation would require decades of research and may run into limits that are not merely engineering problems. The feedback loops between a developing fetus and maternal physiology are intricate and continuous. Whether an artificial system can fully replicate them remains genuinely unknown. That uncertainty matters and should not be papered over, but set it aside entirely. Assume the technology works perfectly. The newborn still arrives into Mars gravity. Skeletal development continues for 2 more decades. Neural architecture continues building. Cardiovascular calibration continues tracking. The artificial womb solves the first 9 months. It does not touch the years that follow. The postnatal gap remains. The cascade still runs. Genetic engineering reaches further. Why not rewrite the human developmental program to expect 38% gravity from the start? Build a version of human biology that treats Mars as its home environment. The proposal misunderstands what development is. Development is not controlled by simple switches that gravity can be removed from, and a different value inserted. It emerges from interactions among thousands of genes, millions of proteins, billions of cells, and continuous mechanical forces, playing out across months of fetal life and years of postnatal growth. Gravity does not appear as an adjustable parameter in any identifiable subroutine. It is woven into the physical environment that development assumes. Redesigning that assumption would mean redesigning human development from first principles, not editing a few genes, rebuilding the process from the ground up. The gap between that ambition and current scientific understanding is not a matter of decades. It is orders of magnitude beyond what biology currently knows how to do. And if it were achieved, what emerges would not be human in any biological sense, meaningful to evolution. It would be an engineered species, designed rather than selected, with no evolutionary history shared with the humans who built the colony. Possibly intelligent, possibly conscious, but a different organism, shaped by human choices rather than by 4 billion years of accumulated selection pressure. Mars colonization, followed to that conclusion, is not the expansion of humanity to another world. It is the quiet replacement of humanity with something else. Terraforming reaches furthest of all. Transform Mars into an Earth-like environment, and the biological barriers dissolve on their own. No centrifuges needed. No artificial wombs, no redesigned genomes, just Mars, remade. The atmosphere presents the first wall. Mars' surface pressure is approximately 6 millibars. Earth's is approximately 1,000. Raising Mars to breathable levels means multiplying its atmospheric mass by more than 150 times. Mars does not have the volatile reservoirs to do this. Vaporizing every polar ice deposit, releasing every sequestered gas in the Martian crust, still falls short by enormous margins. Moving enough atmosphere from elsewhere in the solar system would mean transporting trillions of tons across interplanetary distances. That is not an engineering challenge awaiting a clever solution. It is a resource problem at a scale that makes every other engineering problem in human history look routine. Temperature presents the second wall. Mars receives only 43% of the solar energy Earth receives, because of its greater distance from the Sun. The surface averages around -60 degrees Celsius against Earth's +15. Proposed fixes include orbital mirrors to concentrate sunlight, artificial greenhouse gases released into the atmosphere, large-scale surface, darkening to absorb more heat. Every one of those interventions operates at planetary scale. Everyone requires continuous effort across timescales measured in millennia. Stop the intervention partway through, and the process reverses. Radiation presents the third wall. Mars lost its global magnetic field approximately 4 billion years ago, when the liquid iron outer core cooled and solidified, ending the dynamo effect. No known technology restarts that process. Some proposals place an artificial magnetic structure at the Mars-Sun L1 Lagrange point, a location in space between Mars and the Sun where gravitational forces balance, to deflect solar wind and prevent a rebuilt atmosphere from being stripped away. It would offer incomplete protection against galactic cosmic rays. It would require a structure beyond anything humans have ever built, and it would require indefinite maintenance forever, with no allowance for failure. But the timescale is where all of it collapses. Conservative estimates place Mars terraforming at 100,000 to 1 million years, assuming continuous, uninterrupted technological intervention across the entire span. No equipment failures, no loss of institutional knowledge, no political disruption, no gap in the effort across 1,000 centuries. A colony whose biological foundations are failing within 100 to 200 years from the first Mars-born child cannot wait for a process measured in geological time. A renovation scheduled for completion in 100,000 years offers nothing to tenants who will be gone in a decade. And even a completed terraforming changes everything except the one thing that cannot be changed. Gravity cannot be terraformed. Mars' gravity is 38% of Earth's, because Mars has approximately 11% of Earth's mass. Gravity is a function of mass. No known technology increases the mass of a planet. No orbital engineering, no matter how ambitious, deposits enough material onto Mars to move the gravitational constant. Mars at the end of a million-year terraforming project is a warmer, wetter, breathable Mars. It is still 38% gravity. Every developmental consequence documented across the previous sections still runs. Every bone still forms to the wrong specification. Every heart still calibrates to the wrong pressure. Every vestibular system still references the wrong baseline. The engineering proposals are not failures of imagination. They are serious ideas, examined seriously. But each one repositions the biological barrier rather than removing it. The centrifuge creates Earth-adapted people stuck in a Mars environment. The artificial womb stops at birth and leaves development to Mars. Genetic engineering, at the scale required, produces a successor species, not a surviving humanity. And terraforming runs a million-year clock against a 2-century collapse, then discovers at the end that gravity was never on the table. None of them closes the gap. And all 3 threads of the biological problem are still running. So none of the fixes close the gap. That is the honest conclusion the evidence reaches. And it is worth pausing here before turning toward what is possible, to say plainly what the distinction is that the entire argument has been building toward. Survival and sustainability are not the same thing. They are not even close to the same thing. And every proposal for Mars colonization, at some point, treats them as if they were. Think about what survival actually means. A diver breathes underwater through an apparatus that bridges the gap between biological need and environmental reality. An Antarctic explorer stays warm in a heated shelter, while temperatures outside kill exposed tissue in minutes. An astronaut floats in a pressurized spacecraft, while the vacuum outside would cause blood to boil in seconds. In every case, technology makes survival possible. In every case, the person returns to a world that meets their biological needs without technology holding the gap open. Sustainability means something categorically different. It means maintaining biological function across reproductive timescales. Each generation must develop normally. Each generation must reach reproductive maturity in adequate health. Each generation must produce a next generation that can do the same, indefinitely, without the chain ever breaking. Failure at any link ends the population, not damages it. ends it. On Earth, sustainability is not a project. It is not a system that requires maintenance. The planet provides gravity, shielding, atmospheric pressure, and thermal stability without anyone managing a single process. The inputs human biology requires simply arrive. They have always arrived. They arrived for 4 billion years, while the body's requirements were being shaped around them. On Mars, every one of those inputs would require a technological replacement. Artificial pressure, radiation shielding, thermal regulation, and each system would require continuous perfect operation, maintained by people whose own biological capacity is degrading. The founders might sustain complex systems for 20 or 30 years. The second generation, having developed under reduced gravity and elevated radiation, would maintain them less well. By the third and fourth generations, system complexity would exceed maintenance capability. Failures would compound. The people responsible for fixing the life support systems are the same people whose cognitive capacity has been narrowing for 3 generations. The colony does not collapse suddenly. It thins. It slows. It loses its ability to hold itself together. This is the honest model. Mars can host scientific outposts. Rotating crews of adult humans, on missions of 1 to 2 years, would accumulate meaningful bone and muscle loss and real radiation exposure. Most of the damage would gradually reverse on return to Earth. Full recovery might take years. Some damage would be permanent. But survival, in that framework, is viable. Scientific outposts do real work. Humans add judgment, real-time response, and the capacity to notice the unexpected in ways robotic missions cannot match. Antarctic research stations do this now. Submarine deployments do this now. The International Space Station does this now. The honest Mars presence looks like those precedents. It acknowledges that Mars is hostile, works within that reality temporarily, and returns. But that is not the pitch. Mars colonization is not sold as the Antarctic model. It is sold as the backup plan for humanity's survival. The existential argument goes like this. If an asteroid strikes Earth, if a supervolcano erupts, if civilization collapses in a nuclear exchange, a population established on another world would preserve the human species. Mars is described as an insurance policy, a second copy, a redundant civilization, and if the argument were biologically sound, it would be worth taking seriously. It is not biologically sound. A Mars colony experiencing the multi-generational degradation already traced across this script is not a backup population. It is a dying one, too cognitively diminished to operate complex systems, too physically weakened to sustain necessary work, too genetically loaded to produce healthy offspring, and critically this population fails whether or not Earth ever faces catastrophe. The collapse runs regardless. The backup does not function as a backup because it is not viable on its own terms. Mars colonization, as currently envisioned, does not satisfy the existential argument it claims to satisfy. It replaces one extinction risk with a slower and more certain one. This leaves 2 alternatives that actually align with biology rather than overriding it. The first is orbital habitats with artificial gravity. A large rotating structure generates outward force through rotation, force that functions as gravity for the people and children living inside it. At sufficient diameter, the gradient between head and feet is negligible. Positioned carefully, the habitat can minimize radiation exposure. It can provide every environmental input human biology requires, delivered at human equivalent levels, because the structure was built to those specifications rather than being a planet with the wrong ones. No Mars surface, no Mars sky, but human viable physics. The second is the Moon. Lunar gravity is approximately 16% of Earth's, lower than Mars. But the Moon's advantage is proximity. Crews rotate in months rather than years. Accumulated biological damage is limited because people return before it compounds. No multi-generational residence is required. Lunar resources support industrial development. The Moon does not offer planetary conquest. It offers a nearby working environment where the damage can be managed because the exposure is bounded. Neither of these carries the romance of standing on another planet. They are pragmatic rather than visionary. They acknowledge what humans are rather than proposing to place humans somewhere humans cannot biologically sustain themselves. And that acknowledgement is not defeat. This is the most important thing to say clearly at the close of this argument. Understanding why Mars cannot host permanent human settlement is not surrender. It is not a failure of nerve or ambition. The alternative to understanding is delusion. The alternative to accepting biological constraints is spending extraordinary resources on an impossibility while neglecting the goals that are genuinely achievable. We are Earth creatures, not as a limitation to overcome. As an identity, the body that reads gravity as a developmental signal, that calibrates its cardiovascular system to a specific pressure, that built its DNA repair machinery around a specific radiation background, that evolved its immune architecture inside a specific shielding envelope, is not a body that needs to be transcended. It is a body that needs to be understood. Mars itself remains worth investigating. Whether life ever arose, there is among the most profound questions science can ask. The evidence is in the rock, in the ice, in the ancient chemistry of a world that once had water and warmth, and possibly the conditions for life to begin. Robots pursue that question now. Temporary human scientific missions can pursue it more effectively. The question does not require a city on Mars. It requires curiosity, precision, and patience. All of those are available without sending children to grow up on a world their biology cannot accommodate. Human significance does not require a presence across many planets. It comes from understanding, from experience, from the connections we form and sustain across the brief span of each life. We can explore the cosmos through machines that travel where our bodies cannot. We can comprehend the universe across billions of light years while remaining on the world that built us. The universe is not diminished because we study it from home. And this planet, the only one in the cosmos where human embryos develop correctly, where children grow normally, where generations succeed generations without biological debt accumulating until the chain breaks, is not a prison. It is the instrument that is tuned to the exact frequency our biology can play. Every other world we have found is silent to that frequency. This one is not. Home is where biology requires us to be. For humans, that has always been Earth. Understanding that is not the end of the story. It is the beginning of an honest one.